Dear students, welcome to all of you in the series of design of RCC structural elements. Here today in lecture number 22 we are going to discuss information regarding the compression members, and we will be covering in this lecture introduction part of the RCC column. That means what are the various type of RCC column, their classification, and what are the IS 456-2000 provisions which are applicable in the analysis as well as design of a compression member. Now, first of all, we have to define what is basically a compression member and what is a column. So, as a definition part, we are going to discuss. We can define a structure element that is predominantly subjected to axial compressive forces, and that type of a structure element will be termed as compression member. And regarding column, a compression member which is vertical and subjected to axial compressive forces or axial compressive load, and we will call that type of compression member as a column. And if a compression member which is horizontal or inclined, it will be termed as a strut. And commonly these type of struts or these type of compression members you will be able to see in case of concrete trusses. And the cross-section dimension of a column are in general considerably lesser than their height. So we can say that the height will be greater as in compared to the lateral dimension of the or cross-section dimension of the compression member. A column may be subjected to tensile stresses due to minor eccentricity of the load, because we cannot assure in actual practices that if you are going to design a compression member for axial type of loads, but in practice you will be finding that there is the possibility of eccentricity of the load. So that means load may be having some minor eccentricity, and if that type of column which is subjected to a load having minor eccentricity, so that means it will be subjected to some bending movement, and to that bending moment, ultimately column will be subjected to tensile stresses. But since these columns are called as compression member because the compressive stresses are comparatively higher as compared to tensile stresses, so we can say the compressive stresses will be more predominant as compared to tensile stresses. If that type of condition we are finding in practice, then we will be saying or we will be calling that column is a compression type of a member. So that means column will has to carry compressive stresses, compressive forces, and the design as well as analysis of the column will be taken care as a compression member. Now you can refer clause number 25.1.1 of IS 456. Here let us see how the code is defining a column. So as per codal definition, code is suggesting that a column or a strut will be a compression member, the effective length of which exceeds 3 times its lateral dimension. That means its least lateral dimension. Suppose you have a rectangular type of column and having one dimension may be x and other dimension may be y. So then what we have to check? We have to check that either x is least lateral dimension or y. So whichever is the least lateral dimension, that we have to take into consideration. And as per code is saying that column or a strut we can term it in the category of compression member if the effective length of it exceeds 3 times the least lateral dimension. Now we have to go through the classification of columns, how we can classify the column, what are the various type of classification of columns. So according to clause number 25.1.1 again of IS 456, as we have discussed in the previous step that column or strut is a compression member, the effective length of which exceeds 3 times the least lateral dimension. So in continuation to this, if we refer clause number 26.5.3.1, then it indicates that a pedestal is also a compression member, or you can say pedestal is a compression member, the effective length of which does not exceed 3 times the least lateral dimension. So that means we can just differentiate between these two clauses. First clause gives you the definition of column or strut, and the second type of clause gives you the definition of a pedestal. So all these are compression member, but they have to be differentiated. That means this terminology we have to use. Now, based on the cross-section type, column can be rectangular type of column. That means having cross-section shape as a rectangle. Second type of classification, we can say the column may be a square type of a column. Third one, we can, as per the cross-section, we can classify it as a circular column. And fourth type, which is more taken into account, that is hexagonal type of column. No doubt we can classify in various other types also, but prominently these three type of columns you will be finding in most of the structures, that is rectangular column, square column, or circular type of column. Now another type of classification is classification of column based on the type of reinforcement. So first of all, we can classify it as a tied column. So these are the columns which is having main reinforcement as longitudinal bars, and these longitudinal bars we are tying together or enclosing with closely spaced lateral ties. Now in this diagram you can easily see and imagine that what will be the shape of the column. Now it is a rectangular type of column, and these red color bars are showing the main reinforcement, and these black color rings, they are the lateral ties. So these will be these lateral ties you have to design, as well as reinforcement you have to design, and accordingly we can classify that these type of column which are having rings type of lateral ties, so these type of column are termed as tied columns, and this will be the plan as well, cross-section dimension, cross-section diagram basically. So you can see this is a rectangular cross-section having 4 number of longitudinal bars, and which are parallel to the its centroidal axis, and this black color ring which is termed as a tie. So that means you can easily see that all the longitudinal bars are tied together or enclosed within the black color, these ties that are known as lateral ties. And when you see the cross section of that cross section, mean if you are taking any section, particularly if you are taking any section, then this will be the sectional diagram of the column, and these red color bars will be seen as a vertical bars, and these are known as longitudinal bars, and black color wires which you can easily see here, so these are the lateral ties. Now another type of classification is spiral type of column, the column which are having main longitudinal reinforcement bars enclosed within closely spaced and continuously bound spiral reinforcement. So here we can see the diagram. Now it is a circular type of column. So whenever you are going to design a circular column, then we will be going to use either circular type of lateral ties or spiral type of tie. And here you can easily see that some number of bars are inserted in the column as a reinforcement, and the black color circle is indicating it is a lateral tie. And when you see the sectional view of this column, then you can easily see here that this black color black color ties which you are going to see here, they are continuously time the main reinforcement. So that means there is you can compare these two diagrams. Here in the left side of diagram you can see that the lateral ties are continuously, that means it is in the form of a spiral, and in the right side, which we have already discussed, that is lateral tile column. So here the rings are provided at a particular spacing, but here we are just enclosing the bars with a continuous spiral type of ties. We can say spiral type of a reinforcement. So these are the two type of classification of columns based on the type of the reinforcement. Now other interesting classification of column, that is based on the loading criteria. So first of all, let us discuss that column with axial loading. It is concentrically loaded column. So these are the column on which load is applied concentrically. Concentrically mean the line of action of load and the centroidal axis of the column coincide. So then column will be subjected to only axial stresses and no movement is supposed to be present. Now here, let us see this diagram carefully. This is a tie type of column, and main reinforcement is provided as well as lateral ties are provided. Now this dotted line indicates that it is the centroidal axis of the column, and some load is applied from the top, and this is a compressive type of loads. That's why this column is known as compression member. And we can easily see here that this load is acting along the centroidal axis of the column. So that means this column will be subjected to only compressive stresses, and there will not be any bending moment or tensile stresses. And here we can see easily the pressure diagram of the stress diagram. Now this stress diagram will be in the form of a rectangle. That means you can say throughout the cross section of the column, compressive stresses will be of same intensity. That means uniform stress will be there. But in actual construction, if you observe, this type of condition is not, you can say rarely we can meet this type of condition. This is not possible, as already I have discussed in the previous slide. So however, a little eccentricity may be there, but its effect is not so prominent. So it cannot be considered as per IS 456 guidelines. So you can ignore, or minimum eccentricity you can, later on we will be going to discuss, that can be ignored, and this column will be termed as a axially loaded compression member. Now second type of classification is column with eccentric loading. That means when the load is acting at some eccentricity. So eccentricity means if load is acting away from the centroidal axis. So that type of column on which load is applied at some eccentricity, then along with the axial load, as we have discussed in the first classification, some movement will be also acting due to the eccentricity. And when we are going to design or doing the analysis, then both the axial load as well as the movement due to the eccentricity of the load, we have to take into consideration while doing the analysis as well as doing the design part. Now let us go through the columns which are having some eccentricity of the loading. That means we will be saying that column with eccentric type of loading. Now here we are going to discuss first of all uniaxial eccentric loading. So that means that means eccentricity is having some distance, that means load is acting such that it has some eccentricity from one axis, and the column will be subjected to loading in such a way that either eccentricity from x-axis is 0, but it is not, or you can say it is having some eccentricity about the y-axis. Or second condition can be possible, that it may have eccentricity with respect to x-axis but not having any eccentricity with respect to y-axis. So this diagram will be clarifying what we have discussed in this first type of uniaxial eccentric loading. Generally, this is the column which is having some centroidal axis. That is the centroidal axis which we are going to discuss. Now, if the load is acting, you can see here load is acting at a distance, some distance away from the centroidal axis. Now, what will happen? What will be the effect of this type of loading? So, if it was not having any eccentricity, then your loading diagram, as we have discussed in the previous case, it will be just as a uniform type of a pressure, uniform type of stresses. But now, since we are applying the load at some eccentricity, and due to that, some bending moment will be acting, and that bending moment will be due to this eccentricity. That means if this is the moment M, then we can say this moment M is equal to load into eccentricity from the centroidal axis. And due to this bending moment, now bending stresses will also came into exercise. So you can see here. Now this pressure diagram or stress diagram is changed. Here some stress is there, but if you compare stress at this side, then this stress is greater than stress along other side. So that means there is triangular type of a distribution of stress. So when you are going to design this portion, then you have to design it according to this much stress. And when you are going to design this left side portion, then you have to take into consideration. So that means this eccentricity of the load will be providing some extra stresses due to the movement. Now let us revise the topic. First of all, if there is a concentric type of loading, then this will be a rectangular column or a square column. Now this x-axis is parallel to one side and y axis is parallel to another side. Now if the load is acting exactly at the center of the centroidal axis, that means where these two axes are meeting, then no bending moment will be there or no movement will be there, and therefore stresses will be uh, uniform, or we can say it is a concentric type of loading. Now here you can see easily that load is placed away from the centroidal axis. Now this load is having some eccentricity, and load is acting on the y-axis and having eccentricity EY. So accordingly there will be some movement will be acting and stresses will be there. So this type of eccentrically loaded column is known as uniaxially loaded column. You can see here it has eccentricity only with respect to x-axis, but no eccentricity with respect to y-axis. And then this diagram easily justify or clarify that you can consider when the load is acting at some eccentricity, and you can superimpose these two diagrams. That first of all you can consider the load is acting at the centroidal plus some movement is acting in the clockwise direction or in the direction based on the eccentricity of the loading. So this type of loading, we can say it is a combined type of loading, but it is a case of a uniaxial eccentrically loaded column. Now what is column with eccentric loading but biaxial eccentric loading? So that means it indicates itself that load will be acting such that, or you can say column will be subjected to loading in a such a way that it has eccentricity with respect to y axis as well as having some eccentricity with respect to x axis. So this diagram easily clarify all the steps which we are going to discuss. This is a x-axis which is parallel to one side of the cross section, and y is the another parallel to another side. Now if load is acting somewhere here, you can easily see here this point. If you take a straight line parallel to x-axis, then it will give you some eccentricity that is equal to EY. And when we are taking or drawing a line through that point of application of load which is parallel to another axis, it will be giving some eccentricity from that axis, that is Ex and Ey. So we can say this column is, however, it is symmetric type of column, but loading is acting in such a way that load is having eccentricity from both the axes. So we can say that this column will be subjected to biaxial eccentric loading. So these type of columns are subject to loading in such a way that load is having eccentricity about the mutually perpendicular plane through the cross section of the column. Now this column will be subjected to axial load, of course, as well as movement about both the axes. One will be movement about x-axis, that is mx, and my is the movement about y-axis. Now when we are going to do the analysis as well as design, it will be done considering a column is subjected to combined type of stresses. That means both type of stresses will be acting, and later on we will be able to understand it more clearly. Now let us classify the columns based on the another parameter that is known as slenderness ratio. Now first of all, what is slenderness ratio? Columns can be classified based on its geometrical dimensions, and that geometrical dimension give you one ratio that is known as slenderness ratio, and we can say they are classified based on geometrical dimension. A geometry of the column significantly control the failure type of the compression member. Now how it is? Let us first of all define what is slenderness ratio. So slenderness ratio of a compression member is the ratio of its geometrical dimension, which we can say it is the ratio of its effective length to its lateral dimension. Slenderness ratio provide a measure which indicate the failure of the column by elastic instability. So that means whether column is going to fail by buckling or whether it is going to fail by crushing. So that will be decided based on the slenderness ratio. So formula for slenderness ratio will be L effective, that means effective length of the column, which we will be going to discuss later on, that what is the meaning of effective length of column, and it is to be divided by R, where L is the effective length of the member. You can refer table number 28 of IS 456, and R is the radius of the gyration of the cross section. Now as per clause number 25.1.2, column is considered as a short column, that means it is one classification, when the slenderness ratio about both the axes, which you can write it as Lex by D and Le by V. So that means the columns which are having slenderness ratio about both the axes lesser than 12, those type of columns will be termed as short column. Otherwise, we will be saying it as a longer column or slender column. Now, what is V and D? So you can easily understand here that B is the breadth of the column and D is the depth of the column. That means both are the lateral dimension of the column, and LE is the effective length of the column. If we are saying it is LEX, then it is the effective length of column in major axis, and LEY is the effective length of column in minor axis. Now let us go through in more details what is a short column. So as we have discussed in the previous part, that column having slenderness ratio lesser than 12 is termed as a short column. So a reinforced column, which is a short column, will be failing due to its initial material. So that means if you have a short column and the load is applied on the column, then that column will be failing when its material is getting failed. So if it is made up of concrete, then it will be able to take so much stresses which are lesser than the strength of the concrete from which it is made up. And the load which is supported by the short column is controlled by its dimensional cross section. and the strength of the material of which it is constructed. A short column is considerably, or you can say it is a stocky compression member which is having little bit flexibility. So it is very easily we can understand from these 3-4 points. That means if it is a short column, then that short column will be failing by failure of its material, not by failure by any type of buckling, because it is having very little flexibility. So that means it will be failing just as a compressive with the compressive stresses. And what we commonly observe that a short column fail by crushing without showing any permanent ductility behavior. Now, when we talk about the long column or slender column, so definition part as per IS 456 is if the slenderness ratio is greater than 12, then it will be termed as a slender column. Now, let us understand how a slender column will behave. In slender column or long column, bending deformation will increase. That means load will be, so when load is applied, there will be some bending, or you can say deformation due to bending. And these deformation are termed as buckling of the column. And they will be applying some additional or secondary movements due to which some more bending stresses will be acting. Now, it may reduce the actual load capacity of the column. So if you compare long column with respect to short column, then we can say the load carrying capacity or actual load carrying capacity of the slender column is comparatively lesser than that of the short column. The column which are having high slenderness ratio, so that means they are in other sense we can say having higher length or higher height type of the column. So having higher slenderness ratio, possibility is that they will getting buckle, and when buckling take place, then some lateral deflection also take place, and under relatively low compressive load. So that means if we are talking about the slender column, it is the probability, or you can say higher probability, that it will not fail by compressive loads, but it will fail by deflection, lateral deflection, which is termed as buckling. So when you have to design a slender column, then you have to take into consideration the buckling behavior of the column. And for that, we may be later on going to design a column, and we will be using the formula related to crippling or buckling load of the column. Now let us understand what is the meaning of unsupported length of the column, and for this clause number 25.1.3 of IS 456, it has given some directions. So first of all, the unsupported length of a compression member is taken as the clear distance between the ender strings, except the following some of the condition. So very first condition is if you are using a column below or in the supporting flat slab type of construction. So then what is the code saying? Code is saying that it shall be the clear distance between the floor and the lower extremity of the capital or the drop panel of the slab, whichever is the least. So later on we will be going to understand it with the help of a diagram. The second point code is saying in beam and slab construction, then it shall be the clear distance between the floor and the underside of the shallower beam. So if we are having two beams, then accordingly as per the direction we have to take into consideration the shallower beam, framing into the column in each direction at the next higher floor level. And the third point is a column which is restrained laterally by struts. So it then you have to calculate the unsupported length, then it will be given by the clear distance between the conjective struts in each vertical plane, provided that it has to be having adequate support, and two such studs will meet the column at approximately the same level, and angle between vertical plane through the stud shall not be more than 30 degrees from the right angle. Such studs shall be of adequate dimension and shall have sufficient anchorage to restrain the member against lateral deflection. So this point may not be more valid for our case, and later on we are going to discuss with the diagram also. So fourth type of clause is that in case of column restrained laterally by strut or beam with bracket used at the junction, and then you will be able to calculate by calculating the clear distance between the floor and the lower edge of the bracket, provided that the bracket width equal to that of the beam strut and its least half that of the column. So these two conditions, condition A and condition B, may be more applicable to the design which we are going to discuss in the coming lectures. So now you can see here easily that this column is supporting the flat type of plates. So it is just like a flat plate if it is supporting. Then from the diagram it is very much clear that from the lower edge of the upper flat and the upper edge of the lower flat plate, you can take and you can measure the distance that will be the unsupported length of the column. And the second type of possibilities, if there is a flat type of slab. Now you can see here this is a flat slab, and below that flat slab is a capital, or it may be having a drop panel, or it may be having a capital. Then you have to take the lowest portion, lowest level of that flat slab, which may be either it is a capital or it may be lowest part of the drop panel. So this distance or this height will be considered as the unsupported length of the column. And the third type you can easily see here, there is a column capital is there. So this portion is known as column capital, which is required, and later on maybe in a higher design of concrete structure you will be able to understand it more clearly in case of a flat slab type of construction. And when we are going to design flat slab in your next lecture, next semester, so this will be the length of the distance between these 2 points, and this is known as unsupported length of the column. And fourth type, now you can see this diagram here, two type of beams are there, upper beam and lower beam, and accordingly one will be along y axis and other will be along x axis. So here we will be saying that these are the slabs having beams, and these beams are supported by the column. So according to the diagram, you can easily see along y-axis direction, this is the beam which is having higher depth. So bottom of the beam and top of the base floor, this distance Ly, it will be the unsupported length of the column. And along x direction, you can see that beam is having lesser depth. So Lx can be easily evaluated from the lowest level of the beam and upper level of the floor. So these are the few IS 456 guidelines to calculate the unsupported length of a column. Now what code is suggesting? Code is suggesting some limits, and that is known as slenderness limit. Now it is not slenderness ratio, slenderness limit per column when we are talking about the unsupported length of the column. So for more detail, you can refer clause number 25.3. So unsupported length of a compression member is limited by IS 456. So these are the few guidelines which we are going to discuss. So very first guideline is the unsupported length between end restraint. So that means end supports shall not exceed 60 times the least lateral dimension of the columns. This is one of the conditions which we have to take into mind while we are talking about the unsupported length of the compression member. Second point of discussion is, if in any given plane one end of column is unrestrained, then its unsupported length should not be greater than 100 b square by d. Now what is b? B is the width of the cross section of the column, and capital D the depth of the cross section measured in the plane under consideration. So that means when you are going to calculate unsupported length of column, then you have to take into consideration this clause number 25.3. So that means we can apply a check that unsupported length should not be over than these two conditions which we have discussed so far. Now another important point of our discussion is as per clause number 25.4, that is minimum eccentricity. So as in the start of the lecture I have discussed that no column will be considered as perfectly under axial compressive load because some eccentricity can also be possible. So keeping into consideration those parameters, column when we are going to design, then we have to take into consideration minimum eccentricity. So what code is suggesting, this clause is suggesting a minimum eccentricity need to be taken into consideration during the design of column. So what in actual it says, all columns shall be designed for minimum eccentricity, and that will be equal to unsupported length of column divided by 500 plus lateral dimension by 30. And another condition is it should be subjected to a minimum of 20 mm. And where biaxial bending is considered, then it is sufficient to ensure that the eccentricity exceeds the minimum about any axis at a time or one axis at a time. Now, another point of discussion is effective length of column. So we may define it as the length of the column between the point of zero movement during the evaluation of buckling behavior of the column. And for more detail, you can refer any standard strength of material book in which you will be able to understand it more clearly. Now, effective length of the column depends on the type of end supports. So what are the type of end support? And for calculating or for knowing the value of effective length of column based on the various type of end support of the column, you can refer table number 28 in IS 456 2000. Thank you.